Welcome to the second part of Lesson 4. In Part 2 of our lesson on the chemistry of aromatic compounds, we'll delve into the topic of electrophilic aromatic substitution reactions. This section is important for understanding how benzene and other aromatic compounds undergo chemical reactions while retaining their aromatic core. We'll begin with halogenation, where we'll explore how aromatic rings react with halogens, like chlorine and bromine, to form halogenated aromatic compounds. Next, we'll examine nitration, a process where aromatic compounds react with nitric acid to introduce a nitro group. This reaction is vital in the production of explosives, dyes, and pharmaceuticals. Following that, we'll discuss sulfonation, which involves the introduction of a sulfonic acid group into the aromatic ring. Sulfonation is a key step in producing detergents, dyes, and sulfa drugs. Finally, we will cover carbon-carbon bond forming reactions using Friedel-Crafts reactions. This includes both alkylation and acylation processes. Friedel-Crafts alkylation allows for the introduction of alkyl groups into the aromatic ring, expanding the versatility and utility of aromatic compounds in organic synthesis. Similarly, Friedel-Crafts acylation introduces acyl groups, enabling the synthesis of ketones and other important derivatives. Let's go to the next page and get starting with electrophilic aromatic substitution. Let's discuss the reactivity of benzene through a process known as electrophilic aromatic substitution, or EAS. While benzene typically does not undergo addition reactions, it is quite versatile when it comes to substitution reactions. This is where one hydrogen atom on the benzene ring is replaced by an electrophile. In this type of reaction, the aromatic ring itself acts as the nucleophile. On the slide, you can see several examples of these substitution reactions. Benzene can react to form various substituted aromatic compounds. For instance, it can undergo bromination to add a bromine atom, or chlorination to add a chlorine atom to the ring. Similarly, it can be nitrated to introduce a nitro group, sulfonated to add a sulfonic acid group, or can react to add alkyl or acyl groups, forming alkylbenzenes or acylbenzenes, respectively. These reactions are crucial because they allow us to functionalize the benzene ring. This means we can introduce different groups onto the benzene ring, which can then be used in further synthesis or for various applications in organic chemistry and industrial processes. On the following pages, we are going to look at each of these specific reactions in detail. We will learn about the conditions that make them possible, and also delve into the mechanism for EAS in general, exploring how it applies to each of these reactions. So, let's move on to the next page and get started. Let's start our detailed look at EAS reactions by examining the halogenation of benzene, specifically bromination. Although benzene does not react with bromine on its own, when iron is introduced, a substitution reaction occurs. As you can see in the reaction scheme on the slide, benzene reacts with bromine in the presence of iron to form bromobenzene, with a 75% yield. Bromine on its own is not a strong enough electrophile to cause benzene to break its aromaticity. However, when iron is added, it reacts with bromine to generate a very strong electrophile that can cause a reaction with benzene. The reaction between iron and bromine produces iron tribromide, as is shown in the equation below. The iron tribromide that is formed acts as a strong Lewis acid catalyst. Strong enough, in fact, to break the aromatic stabilization in benzene. The mechanism for this process is shown on the next page. Let's take a look at how iron tribromide generates an electrophile strong enough to break the aromatic stabilization in benzene. As we discussed earlier, bromine on its own is not a strong enough electrophile to react with benzene. However, when iron tribromide is present, it interacts with bromine molecules by acting as an electron pair acceptor, also known as a Lewis acid. You can see the mechanism of this activation process in the scheme below. the iron tribromide catalyst interacts with a molecule of bromine, forming a complex. This complexation pulls electron density away from the bromine-bromine bond, polarizing it. As a result, one of the bromine atoms becomes more positively charged, and thus a much more potent electrophile. But how does benzene react with this positively charged bromonium ion, causing a substitution reaction? Let's move on to the next page, where we will explore the detailed mechanism of how benzene undergoes this reaction. The mechanism can be broken down into two main steps: nucleophilic attack and proton transfer. Step 1. Nucleophilic attack. In the first step, the benzene ring acts as a nucleophile and attacks the activated bromine electrophile. This interaction forms an intermediate known as a sigma complex or rhenium ion. As you can see on the slide, the bromine is now bonded to one of the carbon atoms in the benzene ring, temporarily disrupting the aromaticity of the ring. The formation of this sigma complex is the critical step where the aromatic ring engages with the electrophile. Step 2. Proton transfer. In the second step, the sigma complex undergoes deprotonation. The hydrogen atom that was originally bonded to the carbon atom, where the bromine is now attached, is removed as a proton. This proton is transferred to the iron tribromide complex, regenerating the catalyst and forming hydrogen bromide as a byproduct. This deprotonation restores the aromaticity of the benzene ring, because the electrons in the carbon-hydrogen bond transfer back into the nascent aromatic ring, thus completing the substitution process. This step-by-step mechanism highlights how the presence of the Lewis acid catalyst, iron tribromide, facilitates the reaction by making the bromine more electrophilic, which then allows the benzene ring to undergo the substitution reaction efficiently. By understanding these steps, we can generalize how benzene undergoes functionalization through electrophilic aromatic substitution. The process begins with the formation of a very strong electrophile. This electrophile induces the benzene ring to attack it with its electrons, temporarily breaking the aromaticity of the ring. Once the aromaticity is disrupted, the hydrogen atom attached to the same carbon as the new substituent is removed as a proton. This removal allows the aromaticity to be restored by using the electrons that were originally in the hydrogen-carbon bond. Now, let's move on to the next page and look at the reaction conditions we use to accomplish this reaction in the lab. Now, let's look at the specific reaction conditions required for the halogenation of benzene, focusing on both bromination and chlorination. For the bromination of benzene, the reaction involves treating benzene with bromine in the presence of the Lewis acid catalyst. As shown on the slide, either iron tribromide or aluminum tribromide can be used as the catalyst. The catalyst helps in generating a strong electrophile from bromine, allowing the substitution reaction to proceed. The product of this reaction is bromobenzene. Similarly, for the chlorination of benzene, benzene reacts with chlorine in the presence of aluminum trichloride as the catalyst. Similar as in bromination, this catalyst facilitates the formation of a highly reactive chlorine electrophile, enabling the substitution reaction. The product of this reaction is chlorobenzene. Both reactions follow the same general mechanism we've discussed for electrophilic aromatic substitution, where the catalyst activates the halogen, making it a more potent electrophile. This allows the aromatic ring of benzene to attack the electrophile, leading to the substitution and restoring aromaticity. Let's go to the next page and learn the next EAS reaction of benzene, nitration. Now, let's look at the nitration of benzene, another example of an electrophilic aromatic substitution reaction. Nitration involves the substitution of a benzene hydrogen with a nitro group, which has the formula NO2. Nitration occurs by using nitric acid, which has the formula HNO3, as the source of the electrophile, and sulfuric acid, which has the formula H2SO4, as the acid catalyst. In this reaction, benzene reacts with nitric acid in the presence of sulfuric acid, resulting in the formation of nitrobenzene and water. The active electrophile in this reaction is believed to be the nitronium ion, which is an ion with the formula NO2+. The formation of this electrophile involves the reaction between nitric acid and sulfuric acid. The process begins with protonation of nitric acid by sulfuric acid, followed by the loss of a water molecule, a good leaving group, thus generating the nitronium ion. This nitronium ion then reacts with the benzene ring to form nitrobenzene. Let's go to the next page and look at the process by which benzene reacts with the nitronium ion and undergoes the electrophilic aromatic substitution, leading to nitrobenzene. The process for the reaction of nitronium with benzene begins with the nucleophilic attack. In the first step, the aromatic ring of benzene, which has a high electron density, acts as a nucleophile. It attacks the nitronium ion, forming the sigma complex intermediate. As mentioned earlier, this is also known as an rhenium ion intermediate. During this step, one of the carbon atoms in the benzene ring forms a new bond with the nitronium ion, temporarily disrupting the aromaticity of the ring. Next, the reaction proceeds with a proton transfer step. The sigma complex is relatively unstable and quickly undergoes deprotonation. A proton is removed from the carbon atom that formed the new bond with the nitronium ion. This loss of a proton restores the aromaticity of the benzene ring, resulting in the formation of nitrobenzene. This two-step mechanism, nucleophilic attack followed by proton transfer, highlights the role of the nitronium ion as the electrophile, and the aromatic ring's nucleophilic properties. By understanding these steps, we can appreciate how benzene's aromatic stability is momentarily disrupted, and then restored in the course of the reaction. Now that we've covered nitration, let's move on to the next slide to learn about another important electrophilic aromatic substitution reaction, sulfonation. Let's learn another key electrophilic aromatic substitution reaction, the sulfonation of benzene. Sulfonation occurs by using sulfur trioxide as the electrophile, and sulfuric acid as the acid catalyst. In this reaction, benzene reacts with sulfur trioxide in the presence of sulfuric acid, leading to the formation of benzene sulfonic acid. The active electrophile in this reaction is sulfur trioxide, a highly reactive species. When sulfur trioxide reacts with sulfuric acid, it produces a mixture known as fuming sulfuric acid or oleum. Oleum contains sulfur trioxide in a gaseous form, which is a strong electrophile. A detailed mechanism for this reaction can be found on the next page. Let's go take a look. The mechanism for sulfonation begins with the nucleophilic attack. So, as before, in the first step, the electron-rich benzene ring acts as a nucleophile and attacks the sulfur trioxide electrophile. At this stage, the aromaticity of the benzene ring is temporarily disrupted, as it forms a new bond with the sulfur atom. Following the nucleophilic attack, the reaction proceeds to the proton transfer step. The sigma complex undergoes deprotonation, where a proton is removed from the carbon atom that formed the new bond with the sulfur trioxide. This loss of a proton helps restore the aromaticity of the benzene ring. The resulting anion is then protonated by the acidic environment, forming the final product, benzene sulfonic acid. In summary, the sulfonation of benzene involves two key steps: the nucleophilic attack by the benzene ring on the sulfur trioxide electrophile to form the sigma complex, and the subsequent proton transfer that restores aromaticity and yields the sulfonated product. On the next page, we will begin our exploration of Friedel-Crafts alkylation, where we'll learn how alkyl groups can be introduced into aromatic rings, further expanding the versatility of benzene derivatives in organic synthesis. Alkylation refers to the process of introducing an alkyl group into a molecule, creating new carbon-carbon bonds. In the context of benzene, Friedel-Crafts alkylation involves using an alkyl halide, together with a Lewis acid catalyst, to generate the electrophile, which is a carbocation in this case. The Lewis acid catalyst for these reactions is typically aluminum trichloride. When aluminum trichloride interacts with the alkyl halide, the carbocation is generated, and this is the species that benzene reacts with to form the new carbon-carbon bond. The reaction mechanism for generating the carbocation electrophile begins with an alkyl halide, such as methyl chloride, reacting with the Lewis acid aluminum chloride. The Lewis acid catalyst bonds with the halide, facilitating the formation of the electrophilic carbocation, which in this case is a methyl cation. This carbocation is highly reactive and serves as the key electrophile in the Friedel-Crafts alkylation reaction. Once the carbocation is generated, it reacts with the electron-rich benzene ring, resulting in the formation of a new carbon-carbon bond. The product of this reaction is an alkyl-substituted benzene, such as toluene, where a methyl group is added to the benzene ring. The Friedel-Crafts alkylation reaction is highly versatile and widely used in organic synthesis to modify aromatic compounds by introducing various alkyl groups. Though it is not without its limitations, which we will discuss shortly, this reaction not only expands the range of possible benzene derivatives, but also enhances their utility in producing complex molecules for pharmaceuticals, materials science, and more. Next, we'll have a closer look at the mechanism of Friedel-Crafts alkylation, to understand the specific steps involved in this important electrophilic aromatic substitution reaction. The mechanism for the Friedel-Crafts alkylation begins with the nucleophilic attack. In the first step, the electron-rich benzene ring acts as a nucleophile and attacks the electrophilic carbocation generated from the reaction of the alkyl halide with the Lewis acid catalyst. During this step, the aromaticity of the benzene ring is temporarily disrupted, as it forms a new bond with the carbocation. Following the nucleophilic attack, the reaction proceeds to the proton transfer step. The sigma complex undergoes deprotonation, where a proton is removed from the carbon atom that formed the new bond with the carbocation. This loss of a proton helps restore the aromaticity of the benzene ring. The resulting proton then combines with the aluminum tetrachloride anion, regenerating the aluminum trichloride catalyst, and forming hydrochloric acid as a byproduct. The overall process results in the formation of an alkyl-substituted benzene, such as toluene, when methyl chloride is used as the alkyl halide, where a methyl group is added to the benzene ring. This two-step mechanism, nucleophilic attack followed by proton transfer, demonstrates how Friedel-Crafts alkylation effectively introduces alkyl groups into aromatic rings, enhancing the versatility and utility of benzene derivatives in organic synthesis. Now that we understand the mechanism, let's proceed to the next page to discuss some limitations of the Friedel-Crafts alkylation reaction. Let's discuss 3 important limitations of the Friedel-Crafts alkylation reaction, which are crucial to understanding when and how we can use this reaction in practical applications. One key limitation is that the halide leaving group must be attached to an sp3 hybridized carbon. This means that the carbon atom bonded to the halide, such as chlorine in alkyl halides, must be sp3 hybridized for the reaction to proceed. For example, if we have a halide leaving group attached to an sp2 hybridized carbon, such as in vinyl chloride or phenyl chloride, the Friedel-Crafts alkylation reaction does not occur. In these cases, the electrons are not properly oriented to facilitate the formation of a stable carbocation intermediate, which is essential for the reaction to proceed. Let's go to the next page and look at a second important limitation. Another important limitation of the Friedel-Crafts alkylation reaction is the tendency for polyalkylation to occur. Polyalkylation often results when the initial alkylation product is more reactive than the starting benzene molecule. Once an alkyl group is added to the benzene ring, the newly formed alkylbenzene can undergo further alkylation. This increased reactivity is due to the electron-donating nature of the alkyl group, which makes the aromatic ring more nucleophilic, and thus more susceptible to additional electrophilic attack. For example, when isopropyl chloride reacts with benzene in the presence of aluminum chloride, the product is not just a single alkylated benzene, but rather a mixture that includes multiple alkyl groups attached to the benzene ring. This uncontrolled addition can complicate the reaction outcome, making it difficult to obtain the desired monoalkylated product. Understanding this limitation is crucial for planning and optimizing Friedel-Crafts alkylation reactions to achieve selective monoalkylation. Strategies to mitigate polyalkylation often involve using excess benzene or controlling the reaction conditions carefully. Let's turn to the next page and look at the third and final limitations that we will discuss. Another significant limitation of the Friedel-Crafts alkylation reaction is that some substituted aromatic rings are too deactivated to react. For instance, nitrobenzene is highly deactivated due to the presence of the nitro group, which has the formula NO2. The nitro group is a strong electron withdrawing group, which reduces the electron density of the benzene ring, making it less nucleophilic, and thus less reactive towards electrophilic attack. As a result, when nitrobenzene is treated with an alkyl halide like isopropyl chloride, in the presence of aluminum chloride, no reaction occurs. This limitation highlights the importance of the electronic nature of substituents on the benzene ring in determining the feasibility of Friedel-Crafts alkylation. Electron withdrawing groups deactivate the ring and hinder the reaction, while electron donating groups have the opposite effect. Understanding these limitations is crucial for selecting appropriate substrates for Friedel-Crafts alkylation and designing reactions that achieve the desired outcomes. Now that we have discussed some of the limitations of Friedel-Crafts alkylation, let's go to the next page and learn about a closely related reaction, the Brunstad acid-promoted alkylation of benzene. After that, we will learn about another reaction, the Friedel-Crafts acylation, which will allow us to attach a carbonyl group to benzene. In this reaction, alkenes and strong acids are used to generate the carbo-cation electrophile needed for the alkylation of benzene. The process starts with the alkene reacting with the acid, such as sulfuric acid. The acid protonates the alkene, resulting in the formation of a carbo-cation. This carbo-cation is highly reactive and serves as the electrophile in the subsequent reaction with benzene. For example, when isobutene reacts with sulfuric acid, it forms a tert-butyl carbo-cation. This carbo-cation then reacts with benzene to form tert-butylbenzene, where a tert-butyl group is attached to the benzene ring. This method is particularly useful when working with alkenes, as it provides an alternative route to generating the necessary carbo-cation electrophile for benzene alkylation. Understanding this reaction expands our toolkit for modifying aromatic compounds through electrophilic aromatic substitution. Next, we will learn about the Friedel-Crafts acylation reaction, which allows us to attach a carbonyl group to benzene, further broadening the scope of our synthetic capabilities. Acylation is a term used to describe the formation of a carbon-carbon bond at a carbonyl group. In this reaction, an acyl group is introduced into the benzene ring. The acyl group, denoted as RCO, includes a carbonyl group bonded to an alkyl group. Friedel-Crafts acylation reactions require an acyl chloride, represented as RCOCl, and a Lewis acid catalyst, typically aluminum chloride. An acyl chloride is a compound containing a carbonyl group bonded to a chlorine atom, making it highly reactive and suitable for generating the acylium ion, which serves as the electrophile in this reaction. In contrast to Friedel-Crafts alkylation, which uses alkyl halides, Friedel-Crafts acylation specifically uses acyl chlorides to introduce the acyl group. The reaction mechanism involves the acyl chloride reacting with aluminum chloride to generate the acylium ion. For example, when benzene reacts with acetyl chloride, which is the acyl chloride used in this transformation, and aluminum chloride, the product of the reaction is acetophenone. Note that the carbon-carbon bond forms directly at the carbonyl-carbon atom. Friedel-Crafts acylation is particularly valuable because it avoids the problem of polyalkylation seen in Friedel-Crafts alkylation. The resulting aryl ketones are versatile intermediates in organic synthesis, allowing for the creation of various complex molecules. Next, we will delve deeper into the mechanism of Friedel-Crafts acylation to understand the specific steps involved in this significant electrophilic aromatic substitution reaction. Let's take a closer look at the mechanism for the formation of the acylium ion in the Friedel-Crafts acylation reaction. Here's how the process works. When the acyl chloride is introduced to aluminum chloride, the aluminum chloride, being a strong Lewis acid, coordinates to the chlorine atom of the acyl chloride. This coordination increases the electrophilicity of the carbonyl carbon. As a result, the carbon-chlorine bond becomes highly polarized, making it easier for the chloride ion to depart. This departure of the chloride ion from the acyl chloride leads to the formation of an acylium ion, which is a positively charged species. This acylium ion is stabilized by resonance, where the positive charge can be delocalized over the carbon and oxygen atoms. The chloride ion that was released then forms a complex with the aluminum chloride, generating aluminum tetrachloride anion. The formation of the acylium ion is a crucial step in the Friedel-Crafts acylation reaction because it acts as the electrophile that will subsequently react with the benzene ring to form the acylated aromatic compound. Let's go to the next page and look at how that part of the mechanism works. The second part of the mechanism begins with a nucleophilic attack by benzene. In the first step, the electron-rich benzene ring acts as a nucleophile and attacks the acylium ion, which was generated from the reaction of an acyl chloride with aluminum chloride. During this step, the aromaticity of the benzene ring is temporarily disrupted, as it forms a new bond with the acylium ion. Following the nucleophilic attack, the reaction proceeds to the proton transfer step. The sigma complex undergoes deprotonation, where a proton is removed from the carbon atom that formed the new bond with the acylium ion. This loss of a proton helps restore the aromaticity of the benzene ring. The resulting proton then combines with the aluminum tetrachloride complex, regenerating the aluminum chloride catalyst and forming hydrochloric acid as a byproduct. The overall process results in the formation of an aryl ketone, such as acetophenone, when acetyl chloride is used as the acyl chloride, where a carbonyl group is attached to the benzene ring. This two-step mechanism, nucleophilic attack followed by proton transfer, demonstrates how Friedel-Crafts acylation effectively introduces acyl groups into aromatic rings, enhancing the versatility and utility of benzene derivatives in organic synthesis. That concludes the second part of Lesson 4, where we explored the important EAS reactions of benzene, wrapping up with the Friedel-Crafts alkylation and acylation. In the next part, Part 3, we will discuss functional group directing effects. Specifically, we'll learn how different substituents on the benzene ring influence the position where new substituents are introduced during electrophilic aromatic substitution reactions. This knowledge is crucial for predicting and controlling the outcomes of aromatic compound reactions.